Hey guys, so today we're going to go over question number 1 on your absolute dating practice worksheet. Um, let's get started. So, question number 1 is asking the data table below shows the projected percentages of radioactive isotope X remaining and its disintegration product Z forming over 6.5 billion years. The graph shows the disintegration of radioactive isotope X. So, what this is basically showing you is a radioactive isotope. For example, carbon 14 is an example of a radioactive isotope, and its disintegration product, the product that it turns into when it becomes stable, and the time it takes for the product to form and the radioactive isotope to decay. Okay, so A is asking on the grid below, construct a line graph by plotting the percentages of disintegration product Z forming over 6.5 billion years. Connect all 6 points with a line. The percentages of radioactive isotope X have already been plotted. So this graph is showing our graph for radioactive isotope X. They already drew that graph for us. So as expected for any radioactive isotope, with each half-life, that isotope's amount should go down just like the graph is showing, which means if we have to plot the disintegration product Z, I know the product or the stable product that any radioactive isotope will create will start to go up, right? It will increase exponentially in a curve. So if I plot the disintegration product Z on the same graph, it should look something like this. So go ahead and pause this video and complete question number 1A. Your graph should look something like this. This is the disintegration product line, and this is the radioactive isotope X line. So asks, identify radioactive isotope X. So to identify any radioactive isotope, all you need to know is its half-life. How long does it take for half of that sample to become stable? So for this radioactive isotopes X, we're starting with the 100%, and for it to become half of what it is and turn into the disintegration product, so going from 100 to 50, radioactive isotope X takes 1.3 billion years. So the half-life of radioactive isotope X must be 1.3 billion years. Let's go to your reference table page 1 to see which radioactive isotope has a half-life of 1.3 billion years. And if you go to your reference table, you'll see that potassium 40 has a half-life of 1.3 billion years. And so my radioactive isotope X must be potassium 40. These are your options on how to write it. You can say potassium 40, you can just write 40K, you can write K40. Please do not just write K alone because K40 is the isotope. K is potassium, but a more stable version of K40. So make sure you have all the numbers exactly like your reference table. C is asking, calculate the amount in grams of an original 300-gram sample of radioactive isotope X remaining after 3.9 billion years. Okay, so I start with 300 grams of my isotope X. I want to know how much I have left after 3.9 billion years. If I go back to my chart, I see after 3.9 billion years, I only have 12.5% of my radioactive isotope X left. So all I need to do is do some calculation to figure out the percentage left of any isotope. And if you're given the sample of how much you already have, you just write the amount you have, in this case 300 grams, and multiply by the percentage divided by 100. So in this case, I start with 300 grams multiplied by my percentage is 12.5, so 12.5 divided by 100. And that gives me 37.5 grams, meaning I started with a 300-gram sample that was 100%. After 3.9 billion years, I'm left with 12.5%. So I'm using my starting amount and I'm multiplying that by 12.5 divided by 100 to get 37.5 grams. This is what I have left of carbon 14. So go ahead and try questions 2A, B, C, and D.